Here we go. This is Kung Fu Review number 7 video on equilibrium. So we're going to go through all the key things. Equilibrium is a huge part of the AP exam, so this is really important. Key thing is equilibrium is when the rates of the reactants and the products are being formed at the same rate. So basically what's happening is the forward reaction and the reverse reaction are occurring at the same rate. Therefore what happens is you see no change in concentration. It's dynamic. Things are happening, but they're happening at the same rate, so they pretty much cancel each other out. We reviewed kinetics already. Kinetics is when concentrations are changing. So really key highlight is what you want to be aware of is equilibrium is when the concentrations remain flat. Graphically, they're not changing because the forward and reverse reaction rates are equal. Key things that you want to remember for this is the law of mass action. Remember, products are going to go on the top, so you want to label that in your box in your notes. Products are on top, so you use the coefficients as exponents, and reactants are on the bottom. The other key thing you want to take note of is no liquids or solids. So in your little note box, remember no liquids or no solids are present in equilibrium expressions. We don't count them. So keep that, write that in your little note box right there next to that. Then it's basically Kc or Kp, either one of them. You basically have the reactants, the products on top, reactants on the bottom. Use the coefficient, plug it in, and you can calculate the equilibrium constant using the expression. Solids and liquids never appear in the equilibrium expression. We already talked about that. Next thing, one key thing in this equation is included in your booklet is if you're given Kc or Kp, you can convert from one to the other. See, Kp is an atmosphere, so that's basically when you're using atmospheres, you have a Kp. Kc is molarity and concentration. This equation is in your AP booklet. Key things you want to remember and you want to write down on your little note thing is it's product moles minus reactant moles. That is how we get our delta N. So it's the number of moles of gaseous products minus the moles of gaseous reactants. That's one key thing. Another thing is since P has atmospheres in it, the R that we're going to use is 0.0821, the gaseous R. Since atmosphere is included, that would be that. The other key thing is temperature has to be in Kelvin. Whenever you're using R, you have to use your temperature in Kelvin. And then it's just a matter of plugging in, getting your exponent based on the product moles minus reactant moles, do your calculations, and then calculate Kp. Either find Kp using Kc or the other way around. Next thing, flipping a reaction. We did it kind of like Hess's law of thermodynamics. In equilibrium, when we manipulate K, we can do a couple things. We can flip a reaction. In this case, it's different than Hess's law. If we flip a reaction, we take the inverse, so we basically flip K. Flip a reaction, flip K. That's a key thing you definitely want to write down, jot down on the side there. If you multiply or divide, you basically raise K to that exponential power, so it automatically becomes an exponent. Multiply by 2, that means you're squaring something. Multiply by 3 means you're cubing something. So they have this on the exam in the multiple choice and the free response quite frequently. In fact, here's one from a FRQ. It says calculate the value for Kp of the reaction right here is 8.3 times 10 to the negative third. This is my reaction. They want to know what would the Kp be for this reaction. First thing I check is to check to see if the reaction has been flipped. So if I look here, I have NH3 on the left. Now I have NH3 on the right, so it has been flipped. So the first thing I do is flip K. So I'm going to go 1 over 8.3 times 10 to the negative third. I get that. Last check is check the coefficients. Coefficients haven't been changed, so I haven't really multiplied or divided by anything. So that would be equal to my answer. I would pop that in and get that into my calculator. The other thing that happens is if you need to have two reactions. They do this very rarely, but they do it in the multiple choice. They'll give you one reaction with the Kp here, another reaction with the Kp here, and then they'll give you a target reaction asking you what the K for this would be. Very similar to Hess's law, except instead of adding, like in Hess's law, we get the delta H's here, and we would add them when we did thermochemistry. That doesn't happen in this one. So the key thing you got to keep in mind is that you multiply them together. So I get them to match the target reaction. So if I look right here, first thing I'm going to use is kind of like a compass. NH4HS is on the same side, so it is on the correct side. But if I notice the coefficient of my target is 2, this only has a coefficient of 1. So anything I do, I would multiply this whole thing by 2 to get basically coefficients. So this would be 2, this would be 2. I get 2 is all there. And then what I have to do to this thing, I would square it. So it would be 8.3 times 10 to the negative, 8.3 times 10 to the negative third squared. Then I look at my bottom reaction. If I notice in my bottom reaction, I have N2 could be my compass, and it is on the correct side. On the correct side, therefore I don't need to flip it, and the coefficient matches, so I don't really need to do anything like that. My K is good to go. So how would I get my overall KP? Well, all I would do is multiply these two values together. I would take 8.3 times 10 to the negative third, square it times 3.1 times 10 to the negative fourth, and I would end up with my KP value. So if you're taking K's, you're flipping equations, getting them to match, because if you notice this all cancels, because if you notice right here I have N2 drops down, H2 drops down, I have 2NH3 on this side, 2NH3 on this side, so this cancels, and then I have the 2HS drops, that drops down, and then finally that drops down, so it equals my overall target reaction. You wouldn't really need to take it that far into multiple choice. Be aware of that's what you do with K values. You multiply them to equal a target reaction. K. Meaning of K. It says if K is greater than 1, it means it's product favored. So this is an example of K being large. A large K means we have a whole bunch of products. This is what I want you to write down in the box. Whole bunch of products and very little reactants in your ratio. If you notice here, the green molecules represent the products. If you have a lot of products, that's what we think about. Remember, if something's delta G is negative and we say it's thermodynamically favored, it means this sucker, this reaction is going to go forward a lot, which makes a lot of green and a lot of very little reactants. So when we have a K, a large K is considered greater than 1, it means we have a lot of products compared to reactants. So it's very thermodynamically favorable reaction. So those two kind of things go together. If you have a small K, what does that mean? I have very little products. I want you to write this down. And a large amount of reactants would make my K less than 1. So my K would be less than 1. It would be a very small value. So it could be something like 4.0 times 10 to the negative 8 or something like that. The way that gets is because really it's not thermodynamically favored. My delta G would be positive. Very little of the reaction happens, if at all. You only basically produce one molecule product, which means I have a lot of reactants compared to very little products. So when they give you a K value on the exam, they ask you to interpret it. It tells you two things. It tells you how many products you're going to have compared to reactants. It also will tell you, you can tell if the reaction is favorable or not. Because if it's favorable, it's going to go forward. If it's not favorable, it's going to kind of stay put. All right. Remember during the school year, I taught you about equilibrium, and equilibrium's a place like SeaWorld. I drew Florida on the map, and then we were in Boca, and we were trying to figure out if we were driving to SeaWorld where we were at. Q is basically telling us where we're at. It's the exact same expression as equilibrium, no different. Products on the top, reactants on the bottom, coefficients are exponents. You plug the numbers in. The difference with Q is they give you all the numbers, you calculate it out, and you compare it. If Q is larger than K, like if SeaWorld is 190 miles away, and we drove 225 miles from Boca, we know we would have to go back. So when Q is larger than K, the reverse reaction occurs. If we're at SeaWorld is 190 miles away, and we're here, and we've only driven 150 miles, that means that the reaction must go forward to reach equilibrium, and then if K and Q are equal, it means we are at equilibrium. Here's an example from an AP exam. First thing they ask you to do is write the expression. Well, equilibrium expression, products over reactants. Notice there are gases and it says Kp. I can't use brackets, so I would go NH3 parentheses 2 over N2 to the first, and then I don't even have to write that, H2 to the third. That equals Kp. That's how I write my expression. Second thing is they ask you to calculate the value of Q. So all you're doing when you're doing Q is you're given all the values. Like, for example, NH3 is 0.224. So you see it right up here. So I go 0.224 squared goes on top. My value for H2 is 0.903. So 0.903 to the third. And then finally, my N is 0.411. Plug that in my calculator, and I get a value of 0.166. 3 sig figs going in, 3 coming out, so I get 0.166. Well, that's where I compare it to my K. They tell me my K is 3.1 times 10 to the negative fourth. If my K is 3.1 times 10 to the negative fourth, my Q is much larger than my K. So the first thing I do, it says predict the reaction which is going to go. So on my exam, I would say Q is larger than K. Therefore, the reaction is going to go left or reverse until it reaches equilibrium. That's where it says where you justify your answer. This is saying you've looked at Q and K and you know what the difference is. Left is saying that you know that since you're past equilibrium, it has to travel that direction or reverse. That's what it's talking about in a typical Q problem. Le Chat, remember Le Chat is where we basically shift reactions. When you place stress on a system, it causes it to shift to restore the ratio. It's all about the ratio. In equilibrium, whichever direction the reaction shifts, that side increases the species concentration. So what happens is if it's, I add something, let's say add away, I put the big arrow this direction, which means the amount of reactants would increase because the direction I go with my big arrow basically tells me that I'm creating more of that and reducing the amount of the other one. Three factors in Le Chat. First is concentration. Whenever you add, remember add away, it goes the other way. Increase causes a shift to the other side of the equation. If you take, you go towards. So if I remove something, I always go towards that, which means shift towards that side of the equation. If we look here, temperature. Exothermic means heat is on the right-hand side. Endothermic means heat is on the left-hand side. And it's still add away, take towards. So if I told you I took an exothermic reaction and heated it, or added heat, it would shift this direction. Because if I add, it shifts away. Now remember, we talked about P over R, products over reactants is equal to KEQ. Remember, temperature is the only thing that changes K. Only thing. And what happens to the products happens to KEQ, because they'll ask you. So since the amount of products is decreasing, the amount of reactants is increasing, my KEQ for this reaction would be decreasing as well. Okay? The last factor is pressure and volume. Remember Boyle's law. Pressure and volume are inversely related. So if pressure goes up, volume goes down. Key thing you memorize is when P goes up, you go towards the smallest number of moles. When P goes down, you go towards the largest number of gaseous moles. So it helps to look at an equation and figure out the moles of gases on the left and the right. It helps with Le Chat. Last thing is, on equilibrium problems on the AP exam, they typically will have you do a ICE table. So if you look right here, it says hydrogen sulfide decomposes. 3.4 sample is introduced into an evacuated rigid container that's 1.25 liters. Heated, and 3.72 is present at equilibrium. That's the key, because if you look at it, remember they're always going to give you an equilibrium value, so you back solve. That's what back solving is. Remember, we're going to use molarity. You're only going to use either molarity or atmospheres in a table. So key things for ICE problem table you want to write down is, one thing is you're either going to use molarity, has to be either molarity or atmospheres in an ICE table. Second thing is you're always going to use the coefficients. The coefficients of the equation, so 2, 2, and 1 represent your change line. So this is basically 2x, 2x, and this is just x. And then since this is the zero side, other thing, remember the equilibrium always goes towards the zero side. So this reaction is going to go this direction. So what I'm going to end up with is minus 2x plus x. Then my original molarity, I'm given 3.40 grams. I divide by the molar mass, which is 34, which basically gives me 1/10 of a mole. But I have to change it into molarity, not moles. So I divide by 1.25. So 1.25 gets me 0.0800 original molarity. Drop it all the way down, I'm going to get 0.0800 minus 2x. This is 2x, and this is x. That's where they tell me an equilibrium value. They always have to tell you an equilibrium value. Change the color here. I'm going to take 3.72 times 10 to the negative second and divide it by 1.25, because again I need molarity. When I do that, I am going to get 0.0298 is present at equilibrium for this value, which technically that's where I can use algebra So x in this case is not that difficult. It's already pretty much done. X is equal to 0.0298. So my last step then is I basically multiply x times 2 here, getting 0.0595. So I basically plug it into the E line. Then I come over here, I plug in x here. Ultimately, when I'm all said and done, I do the math, I get 0.0205. So what I was able to do is, using the initial value, which is critical, so let's focus here. If you look here, using the initial value, which is 0.08, I got from that divided into that. They're always going to give me an I-line value, and then they're ultimately always going to provide me a equilibrium value, which allows me to find x. And once I find x, using these ratios right here, I drop them into the E line, and ultimately I get the 3 numbers at the bottom, because the last thing it asks for, because if you notice here, it says calculate the equilibrium concentration and molarity for the following gases. What's the concentration of H2? 0.0595. Concentration of H2S is going to be 0.0205, so I get the points for that on the exam, points for that. I didn't write the expression. I could write the expression and basically plug these values in, because the last thing they asked me is find the equilibrium constant. Once I find the E-line values, the trick is I just basically plug it into the expression, and I can solve for the Kc value, and then there'll usually be one other part to the add-on of the problem. All right? Hope you guys have a good weekend. I will see you on Monday. Definitely a reaction video quiz. Make sure you study the information that you had to copy down in all the boxes. If you're going to prom, enjoy the prom.